Does this look familiar?
Yeah.
F of g of x?
Yeah.
Okay, write that down. It's called the composition of two functions. You learned about that in pre-calculus. What does this notation mean?
The derivative.
Derivative, okay, so that looks familiar. We've done a lot of this, but you might not have put much thought into the symbolic representation of this. Take a look at that and tell me what you think. We've done quite a bit of this, just not symbolically.
It's definitely a work of art.
Looks good.
No, I want you guys to think about what this means. Okay, keep going.
This would be exactly what we just did. This would be that because you took one equation, you were optimizing the equation, you put it inside of the equation, and then after you solve that equation, you take the derivative of that, and you set it equal to 0.
Okay, so yeah, I see what you're saying. I see what you're saying. We kind of did something like that in the quiz.
Processes, you basically do that like that.
Okay, I see what you're saying. That's a good thought. We put one function into another and took a derivative. Yeah.
I feel like
Let me put it this way, because I've used this terminology quite a bit. Is G inside or outside function?
Inside.
F outside or inside?
Outside.
What is this sounding like? Chain rule.
Oh, I love me some change.
You guys remember the chain rule? We have an outside function and an inside function.
Yep.
So I know we haven't looked much at it symbolically, but how do you take the derivative if you're using the chain rule?
we do the derivative of the outside.
You take the derivative of the outside function and leave the inside function alone,
And then multiply it by the derivative.
and then you multiply it by the derivative of the inside function. Is this looking a little more familiar now?
Yes.
You take the derivative of the outside function, leave the inside function alone. And then you multiply it by the derivative of the inside function.
Now we're going to do some integral chain rules.
Well, that's where I was heading. What if you had an expression like this, and you took the integral of that?
Then you would.
What did you say? Yeah, isn't the integral the opposite process of a derivative?
Yes.
So what would we end up with?
F of G of X.
F of G of X. Yes and no. Plus C, right? Anytime you take an indefinite integral, there's always the chance that there's some weird constant out there we hadn't accounted for. Here's the thing, though. It looks like, well, this is going to work out pretty great. How often do you think you have this situation where you have an outer function and inner function multiplied by the exact derivative of the inner function?
Never.
Do you think you have that very often?
No. Once in a blue.
Okay. So sometimes integration isn't as straightforward. Let me rephrase that. Quite often, integration isn't quite as straightforward as differentiation because you don't have exactly the form that you need. Okay, you might have close to the derivative here, but it might be missing a constant or a variable or something. So that's what this lesson is all about. Okay, you have some kind of expression that looks close to a chain rule, but you've got to manipulate it, change it a little bit so it actually is a chain rule. Then you take the derivative and you end up with some kind of a composition of two functions. You see where we're going with this?
Yes.
Yes.
I am. Thank you, though. So here's a little definition your book gives. Let G be a function whose range is an interval I, and let f be a function that is continuous on I Does anybody have any idea what that's talking about? Yeah, I can see what you're saying, yeah. Go ahead, Ben.
So when it says range, is it like talking about the domain?
Well, that's where I wanted to hit. This word range, I know you've seen it before. Is this an output or an input? Range.
Range is a Y value.
Those are y values. It's an output, right? So g is a function whose output or range is some interval I. Now this phrase right here, let f be a function that is continuous on I. What does it mean that it's continuous? There's no holes in the graph. It's continuous. There aren't any discontinuities. Is that mostly describing the domain of f or the range of f? If it's talking about continuity of a function, is that describing the domain or the range? The domain. There aren't any excluded x values, right? So the range of one function, you guys, I think you can understand this. It's a little complicated, but I think you guys are clever enough to figure this out. The range of one function becomes the input of another function. What is that describing? The range of one function becomes the input to another function.
Inverse equation.
Okay. You guys are pretty close with inverse. I can see where you're...
X becomes Y in inverse.
Let's say that you plug something in for g of x and you get I. That's the output, right?
Yeah.
Shouldn't that be the input for a new function?
Oh, yes.
Isn't that just a composition of two functions? G of x has a certain output. That becomes the input for f.
Yeah.
Yeah.
You guys see what it's saying now?
Oh, okay, now I get it.
So G has some range, and that range becomes the input for f. Because I is the same thing they're describing both times. Okay? So anyway, all they're describing here is a composition of two functions.
Okay, so it's just saying that whatever G of X is what, the solution to that is F of...
Those are your inputs for f. You know?
Okay.
Yeah. So it goes on if G is differentiable on its domain and capital F is the antiderivative of little f. And the only reason I made a big deal about that first part is, quite often if you're reading a theorem put on a board, or if you read a theorem or a definition out of a book, who really puts a lot of thought into it? Honestly. Right? And I'm not saying it's a bad thing. It's just normal. But you may have to be able to interpret this kind of wording on the AP exam. So you need to have a little bit of an understanding how to reason with mathematical language. You guys understand the point there?
Yeah.
So, hey, Fanny Pack Friday.
Yes, sir.
Oh, I should have worn mine. Maddie, where's yours? Yeah.
What?
He's wearing a fanny pack at work?
Gentry hasn't given us ours yet. I was just offered that it's in the car like 15. Really? I just keep saying, not right now, Gentry. It's not even Friday.
Oh.
Can we go today?
Yeah.
Sad story.
Okay.
Did you guys ever talk about how...
So then,
Yeah.
Yeah, we already had
the
it.
integral of f of g of x
He already told us the whole.
times g prime of x dx. What is this looking like, you guys? This right here?
It's looking like the.
Isn't that a chain rule situation?
Yeah.
So if you take the integral of something that looks like it's been chain ruled, I just made up a verb, then you get a composition of two functions, capital F of g of x plus c. And here's actually the main point of the lesson. Letting u equal g of x.
Whoa.
This is what's known as U-Substitution.
Really?
I know it's hard to make sense of symbolic math expressions, so once we start using this with actual problems, it'll start to make more sense.
That's your motto. Write down the stuff, wait till we get into it, and then you get it. I like that motto.
Make that up. I actually think that's actually
Yeah, we'll take a look at that. Now, you guys, hopefully you've seen a little bit of U-Substitution before in pre-calculus. This problem here, for example.
I remember U-Substitution. It's with the substitute. It's with systems of equations.
Do you guys know how to factor x to the fourth plus 10x squared plus 25?
No.
Probably not, but if you let u equal x squared, do you remember something like this?
Yeah, it's the coolest.
Because x to the fourth is really just x squared squared.
I remember learning.
That is u squared.
So that just becomes u squared plus 10u plus
20.
25.
Oh, and we can do
That's
that.
so simple.
5 times u plus 5.
And then you just or unsubstitute, I guess.
X squared plus 5 times x squared plus 5.
So what we did here is we didn't let u equal a number. What u is equal to an expression of x. And that's what it's saying over here in this definition. U isn't equal to a number. U is equal to an expression of x. You guys see the similarities?
Yeah.
Really, that's, I mean, in simple terms, that's what's going to be happening here later on. Okay, so here's example 1. Find the integral of x squared plus 1 squared 2x times dx. What this has to become, you guys, is a matter of pattern recognition. It really has to become a matter of pattern recognition. First of all, does it look like we have an inside or an outside function? We have an inside function here that's being raised to another kind of function that's being squared. So we have an inside and outside, right? That's one thing to try to recognize. And then you have to really be able to recognize, is this a result of some kind of thing that's been chain ruled? Okay? So here's the progression the book makes. Once you guys get good enough at this, you might not have to use this progression. But they would suggest, just to start out, that we're going to let g of x equal x squared plus 1. Okay. What's g prime of x? 2x. Okay. So looking at our expression again, wouldn't this be g of x inside of here? And this would be g prime of x. And isn't g prime, or isn't g inside of another function that's being... So this is an example. A chain rule. You guys following? We have an inside function and an outer function. So what do you guys suggest? Let's see if we can make our way through this. The outside function is this thing that's being, yeah. Look at the definition, you guys. If we're taking the integral of some kind of a function inside of an outer function, and then we have the product of the derivative of that inner function, then what does it equal? It equals the, what is capital F compared to little f right here?
The derivative.
This is, be careful how you say this. What is this?
The derivative.
This is the anti-derivative, or integral, right? Antiderivative is integral. So it's not just that we form a composition of two functions, it's that we form a composition of two functions and the outer function is the integral of the original outer function. So we already know what the inner function is, s squared plus 1. What's the quote-unquote outer function here? Something being squared, right? So if we just kind of imagine that inner function wasn't there and it was blank, how would you find the integral or the antiderivative? You change this to a power of 3. You put it over 3. Okay. So it's going to be x squared plus 1 to the third power over 3. Okay. That's a good thought. I see where you're going with it. But take one more look at this. The whole entire chain rule thing here has to equal that. All we need is a composition of two functions. We need one function inside of an antiderivative. We need the g function inside of the antiderivative. You guys follow what I'm saying? What was the g function? Is that inside of an antiderivative now? So we're done. Except for one thing. Plus c. Well, we needed the 2x here. That's a good question. Did you guys hear that?
Yeah, what?
Did we need the 2x there?
Yes.
We needed it. Keep going. Yeah, we needed the 2x there so that we had a chain rule situation. If the 2x weren't there, this wouldn't have been a chain rule situation.
Oh.
You guys understand? That's really important that 2x
So that takes what you
was there.
Yeah. That first one.
Correct.
Just adds it to this next one.
Okay. Now, you guys, just to prove a point, I want you to do this in your notes. Do this. Reverse the process that we just did and make sure you end up with what we started with. Just so you guys can feel comfortable that we're doing this right. Go ahead and do it. It'll be good practice anyway.
Yeah. Okay.
Take the derivative of that antiderivative.
I think I know what we're supposed to do.
1.
Right?
1.
So we're going to run a chain rule that first.
And the inside function is 2x. There it is. Right there.
Did you take the integral of the derivative of the inside function? It's a chain rule.
Yeah, I got it.
Are these different goldfish?
I got it.
What? These the regular counter?
Did you get
I
it?
have no clue.
Did you guys,
Are you lying?
I mean, I know it's been a while since we've done derivatives, but hopefully we have done enough of them that it's like riding a bike, I don't know.
Giving a hug.
Giving a hug.
Yep, 2x.
What happens to the 3?
Goes down.
3 drops down,
happens so often. Right.
and then you decrease the power. What's the derivative of a constant?
Heartbreak.
So the constant just goes away. But we also need a chain rule part. What's the derivative of the inside?
2x.
The 3's cancel. And isn't that what we started with?
That's exactly.
X squared plus 1 squared times 2x. Here's another example.
Miracle. It's like that movie.
That was a great one.
Again.
Woo! But from the perspective of us, it gets the worst. Like how Russia thinks out here farmers when you say one have a game. All the Russian dudes were doing it's so bad. They're like, it's the dumbest game in the history of hockey. The worst game ever. It's like our country's proudest achievement in the Olympics.
Alright, anyway, come on, let's go.
Okay, you just throw a trig at us like it's
Integral of 5 cosine 5x dx. So,
this is not a problem.
Gabe, do we have a situation here with an inside or an outside function?
No.
Yes.
I'm sorry.
What would the inside function be? So if we call that g of x the inside function, in order for this to truly be a chain rule, we also have to have g prime of x in there somewhere.
And that's 5.
So what's g prime of x? We have that right there. And that's the point I'm trying to make, and hopefully I'm making it, that in order for this to work, you have to have that g prime expression in there. If you have this inside versus outside function, that's great, as long as you have g prime.
How is 5g prime?
Because g of x is 5x, the derivative of that is 5. Does that make sense?
Then if I get
Yeah. So yes or no, is this a chain rule?
Yes, sir.
It is. So let me go back to this definition. If you're taking the integral of a chain rule, then you integrate the outside function to get the antiderivative, and then you just place the inside function inside that antiderivative. Okay? So what's the outside function here?
5 sine.
The outside function is cosine. What's the antiderivative of cosine? Sine. So that's the antiderivative, and now you just place the inside function in. So it's just sine 5x plus c.
And you just get rid of the 5 because you don't.
It had to be there to recognize. It had to be there to recognize this as a chain rule.
As a chain rule.
As a chain rule. So it had to be there to recognize it as a chain rule. But when you take the integral, you just take the integral of the outside function and you leave the inside function alone.
Okay.
It's not really short, guys. It's the way it's done. Now, you guys, if you were to take the derivative of this, what would you get?
5 plus 2.
You'd get cosine 5x times 5. Yes? Okay.
Start in the middle.
Now, you guys, so far this hasn't been too bad, right?
So far.
But it's going to get
Here's another thing you need to consider. I mentioned this, but you might not have heard it. Do you think you're always going to have the situation where you have everything that you need?
No. You're going to
Okay.
find it.
Most of the time you have something where g prime is close, but you might have to tweak things a little bit. Okay? So consider this. Example 3.
This is a tricky one.
So what's isn't this, wouldn't we call that g of x right there? But that means g prime would have to be 2x. We have part of it.
Yeah. On both sides.
So it must have used to been 1/2.
Yeah, you must have used to.
Okay. You guys are hitting the nail right on the head.
Don't nail that.
Well,
Figuring our way out of the locker room.
okay, check this out. If there were a 2 there, wouldn't that be nice? You can't just put a 2 there, though, because we've changed the expression. Here's something to think about. Okay, you guys see that? If I put a +1 here, is it the same or different?
Different.
What if I put a -1 there?
We're good.
Same now, right?
So if you do that all over,
So the point is, we have to do something and then undo that something.
Multiply it by 2 over 2.
We need to have a 2 there.
let's try to put that over.
So we times it by 1/2 out there. You guys see what happened?
Yeah.
We did something here, and we undid that something out here.
Do we just put that back into the forward to
So once you find the antiderivative, that 1/2 goes in front of it. Because didn't some of you mention there had to have been a 1/2 in front of there to cancel out the 2 when it drops down? When you take the derivative, if you were kind of thinking along those lines. So let's just double check though. This is the composition of the 2 functions, right? And that's G prime. So do we have everything we need? We have a composition here, we have G prime. Everything's good to go now, so we just have to find the antiderivative of this outside function. And again, don't worry about the inside function. Just take the antiderivative.
It's like the saddest thing.
You ready, Gabe?
Sorry.
Just take the antiderivative. Just imagine that inside function isn't there. What would you do with the 2?
I'd want her to do it.
You'd turn it into a 3,
Put it over 3.
and then you would divide by 3, and then the inside function just stays what it is.
you put the 2
And then we have the plus c.
So really, just put I squared plus 1 cubed over 6.
So then it becomes x squared plus 1 cubed all over 6 plus 1 plus c.
Remember, that goes to 2x. All we did was put 2x back into the neutral.
Does that make sense, Monica? You had to have the 2x there, so you had a chain rule, but other than that, you don't use it when you integrate. Should we check this, though, just to make sure?
Yeah, let's do it right now. This will be fun.
What do I mean by checking it?
Find the derivative first.
Find the derivative. You guys can do that. You don't have to watch me. Do the derivative. Check it.
Okay.
As you're working on this, I want to make one thing clear, you guys. What we just did works only with integers. You can multiply and then divide by integers. If we were missing variables, let's say we had x squared, but we needed x cubed, you can't multiply by x and then divide by x. Do you guys see the difference? Because we don't know what x is, and we might be dividing by 0. Just weird things could happen. So you can only do this with numbers. Are we clear on that?
We're clear.
Okay.
Clear as we can be.
Clear as we can.
It's not a beautiful February morning.
It is the best winter day that I can remember. Isn't this crazy?
It's like, we'll go swimming today, and it's February.
Try this one from start to finish all on your own, if you can.
We can.
See what you can do with that one.
Yes.
All right.
Plus C.
So I'm assuming you let g of x equal x to the third plus 5, so then g prime would be 3x squared. We have the x squared, so we need a 3 right there and a 1/3 out there. So now we have the 3x squared that we need for g prime of x. So this whole thing now is a chain rule. Yeah. So it's 1/3. And then again, just imagine that's not there. It would be raised to the 5th power over 5, right?
Yes.
Of x to the third plus 5. Plus c. Plus c. Alright? You guys, really important before we move on that you ask questions. If something's not clicking here, then it wouldn't make sense to move on to a new topic. What questions do you have?
When would you use this for? Is this going anywhere, or is this just a skill?
This is a more common way of doing integrals is by is by this kind of a thing. Okay. The common question that I hear is, what happens with that? Okay. If we go back to the definition here, if you take, yeah, you guys need to watch this one more time just so I make sure we got it. If you take the derivative of a composition, you end up with f prime g of x times g prime of x, right?
Yep.
But if you take the derivative, if you take the integral of something that you just differentiated, don't you just go backwards?
Yeah.
Okay, so even though this does have a g prime of x, when you take the integral, you just end up with the composition that you started with. There is no g prime anymore. Okay. All right.
So it gets sucked back into the equation.
Pretty much.
Black hole. Black hole.
Let's consider this one. This will have to be our last example. We're not done with 4 or 5. We'll have to pick this up next time. But
Hey, Mr. Hub,
yo,
are we going to do product and quotient rule and stuff? Integrals?
not so much quotient rule. That's more PC.
Okay, that sounds insane.
You guys remember last year in pre-calculus when you had to do what's it called? Partial fraction decomposition.
Oh, yeah.
Yeah.
That's
Is
kind
that
of
the
like
A, B, C thing?
that's kind of like the quotient rule for integration. But that's part of calculus BC.
And we hate those guys.
Yeah. We don't actually.
We think we're nerds.
Okay.
Like nerds.
It just goes a little further and faster. This is a different way of doing it. Change of variables. You guys remember that factoring problem I showed you where we let x squared equal u? And we changed the variable. Didn't that make the problem easier?
Yeah.
So where am I going with this?
We're going to change all the x's into y.
Is there a substitution we can make here?
Yeah, we can change that parenthesis into, we can change that radical into a parenthesis 2x minus 1 to the 1/2.
We could, yeah. And we're probably going to do that a little bit later.
So then when you substitute
Not now.
But I'm talking about making a substitution.
So change dx.
Okay, let me ask you this, you guys. Don't write this down. Would you rather try to find the integral of this or the integral of this? Which one would be easier to take the integral of?
The bottom one.
Obviously this one, right? So what if we let u equal 2x minus 1?
Wow, just let you do whatever it wants.
Right? Now you guys, we're starting to unravel here a little bit. You got to hang with me on this. This is a brand new topic, and if you don't hear it right the first time, how are you ever going to understand it? What does du equal? Du is the derivative of this, so it's just okay. Now hold on a second. You guys are right and wrong. Not wrong. What did we take the derivative with respect to?
dx.
So shouldn't this really be du dx? So I don't want the dx over here. We want it over there. We took the derivative of u, but with respect to what? That's why we have to have the dx. Okay. Now, here's the thing, you guys, and I'm going to try to explain this real slow. I want to change this whole entire thing right here into just expressions involving u, no x's. So we can certainly make a substitution. We can certainly make a substitution here for u, but wouldn't that still leave us a dx? I want to have dx there. Did you guys hear that? We're not just substituting here, we also have to substitute here because I don't want to have a dx there. What does dx equal? Dx equals du over 2. Now we can completely substitute out all the x variables and have just u variables. So this turns into the integral of the square root of u times du over 2. Now it's looking easier, but doesn't it still look a little unusual?
Yeah.
Would it look more usual to have this?
Yeah, much more usual. So you can put a 2 on the outside and you'll get rid of them, right?
Can you do the negative?
That's not a bad thought. Do you remember the property of integrals? If we were taking the integral of 5x, couldn't you just move the 5 out of the integration process?
Yeah. If you wanted
So
to.
can you do the 1/2?
So we can just move the 1/2 out of the integration process.
So close.
You were close. You had the right idea.
So close.
But you can just move the 1/2 out of the integration process there. And doesn't this look pretty easy to integrate now? Square root of u du.
Yeah, it does.
So this, I would now make this suggestion. I don't know who made it over there. Braden, I think, made it. 1/2. Should we change that to u to the 1/2 instead of the square root of u?
Yeah.
So now integrate. What's the integral or the antiderivative of u to the 1/2?
2u to
2u.
1/2 over.
Say that one more time.
2u to the 3/2 over 3.
You guys all right with where that came
And
from?
those 2's are going to cancel.
And then we still need something there. Plus c.
But then we got to change u back to the original.
And the 1/2 and the 2 would just cancel.
So that gives us 2x.
And then we just unsubstitute our substitution. What was u originally equal to? So it's 2x minus 1 to the 3/2 over 3.
Why would that be easier than just not substituting and just doing the chain rule?
Well,
Oh no, because you'd have to get a g prime of x to do it.
I'm not saying this was an easier process for this particular example. We could have just multiplied by 2 and multiplied by 1/2 out here. But the more complicated these integrands get, trying to figure out what to multiply here and what to divide here, it gets much more complicated. So I'm just telling you guys, this U-substitution, I know it seems more difficult because it's new, but it is a lot easier than trying to figure out, well, what has to go here and then here and here. It just,
It's money.
make the U-substitutions. Okay? We'll have to pick this up next time.
I'm gonna try to go back and